Our goal is to follow the branch as it goes around the saddle node bifurcation. And we realized that in order to do that, we may have to parameterize that branch in a different way than simply by the bifurcation parameter. So let's draw that first and then see how we implement it. Okay, so we have a bifurcation diagram with bifurcation parameter lambda. And so let's assume we have a branch of solutions which undergoes a saddle node bifurcation. And we want to follow that. And following means that we imagine we have a solution here. So that would be a solution x of S0 and lambda of S0. And we're trying to find the solution further along that branch. So we have this parameter S, which we mean to vary along that branch. So it's sort of measuring like an arc length. And so the idea is that we now first determine a tangent to that branch at the point where we are. Let's draw that tangent. So here's a tangent vector. Let's call that tau. And so we extrapolate along that tangent vector a certain distance all the way to the value s. We go from S naught to S. And of course, that will not be on that branch anymore. And so then what we want to do is we want to put a plane perpendicular to that tangent like this. And we want to find the solution on that plane for that branch, right? So, so we're going to do the following steps. We're going to calculate the tangent, and then we define the equation for the plane that's perpendicular to the tangent at this distance s, and then we solve that equation simultaneously with the equation for the branch. Okay, so we first need a tangent, and so we imagine our solution is given by x of s and lambda of s. And the tangent vector will therefore be dx by ds, d lambda by ds. So how is that defined? Well, we know that along that branch, you always have the function f of x and s, and lambda of s is equal to 0. That defines that branch. And so if you take the derivative of this with respect to s, we get df we get a gradient with respect to x times dx by ds plus the gradient with respect to lambda, d lambda by ds. Or in other words, and this is 0, right? Because all along the branch, f is equal to 0, and so the derivative along the branch must be 0. And so we see we can write this as making a new extended Jacobian, which consists of the Jacobian fx, and together with this column f lambda, times x dot, lambda dot, where dot stands for the derivative with respect to this arc length parameter s. And so that defines our tangent vector. And we want to now normalize the tangent vector. So we would have tau is equal to x dot lambda dot divided by the norm of x dot lambda dot. Okay, so then the norm of tau is 1. Good. Okay, so we have a tangent vector. So now we need the equation for that plane perpendicular to the tangent vector at a distance s. And so if I now add an arbitrary point on that plane, so if I take an arbitrary point on that plane, the projection of that vector, let me not draw it, let me just mark it. The projection of that vector onto the tangent vector is this length, right? And so that tells us that the equation for all those points on that plane is given by, well, we project the vector, which is x of s minus x of s0, that comma lambda of s minus lambda of s0. So that's this vector from here to here projected onto tau. So this transpose times tau, that is equal to this length here, which is s minus s0. So that defines our plane. And so we need to solve this equation together with the equation for the branch itself. And so to do that, we define a function h, which we set equal to 0. So we want to have now a new variable, which is the variable x comma lambda. And we introduce this function h of y, and s is a parameter of it. And for all s, we want to have this to be 0. So that should define our the condition for being on the branch. And so now we have, and h is given by, on the one hand, we require that the point is on that branch. So it must be f of y must be 0. And at the same time, we need to have that point to be on that vertical plane, that vertical perpendicular plane. So we get tau times x minus x. I mean, I wrote it above, I wrote it actually at x of s minus x of s0, comma lambda of less s minus lambda of s0. This minus s0 has to be 0. So that's the condition that we need. To follow now that branch continuously, smoothly by varying s, we essentially need to invoke again the implicit function theorem, like we did in the original problem when you just said, well, we're looking for a fixed point and want to continue it along that branch. And we noticed, okay, in order to do that, we need to have that the Jacobian fx is invertible, which is not at this bifurcation point, right? So now what the new problem is that we have defined a new equation which follows now the branch, not when varying the bifurcation parameter, but instead this parameter s. And again, we need that we can follow that, continue this solution uniquely and smoothly as we vary s, without ever the Jacobian becoming singular, right? So we need to show that the Jacobian of this h is actually not singular. So what is the Jacobian of h? Let's see. So we have the Jacobian, and we need to be clear with respect to what. S is a parameter, so it's just h is actually a function of y. So we need the Jacobian of h with respect to y. And so we get a big matrix where the function f depends on y, which depends on x and lambda, I mean, which is x and lambda, right? So we have here first the derivative with respect to x, which is a matrix, the original Jacobian. And then we have this vector the derivative f with respect to lambda. And then we have the bottom row where we also need to take a derivative with respect to x and with respect to lambda. And so there, if it's with respect to x, we get a tau. And with respect to lambda, we also get the other component of tau. Tau has a component with respect to x and a component with respect to lambda, right? So that's what we had up there. Tau has x dot and a lambda dot. And so let's write that down. So we get here, we get a tau with this, a tau x component and a tau lambda component. And we need to show that this is not singular anywhere. Well, the question is really, is it singular at that bifurcation point? So let me mark the bifurcation point with superscript 0. That's at the parameter S0. And so what do we know there? First, this is, what kind of object is this? This is n dimensions, n rows, but n plus 1 columns, because we've appended that vector f lambda. And so we know that at the bifurcation point fx is singular, but we are assuming that the singularity is actually a fold point, meaning the rank of that matrix is actually n minus 1. So this has n minus 1 linearly independent rows or columns. The f lambda, what do we know there? Well, we know that the tangent vector is defined by the scalar product of fx f lambda with respect to the tangent vector. So that means this thing here has a rank n minus 1. A rank n rather, because let's see, wait a minute. Right, it has one. Oh, shucks. So we need to show that this is not singular, so that it has a rank of n plus 1. So this is n rows and n plus 1 columns. We know that fx is singular when we assume it is a fold point, and therefore it has a rank of n minus 1. Also, because it's a fold point, f lambda is not in the range of fx. So therefore, fx has n minus 1 linearly independent columns, and f lambda is linearly independent of all of those. So the whole top part has n linearly independent columns, and therefore also n linearly independent columns. Then we know that this tangent vector satisfies this orthogonality. It's perpendicular to all the rows in the matrix fx f lambda in this Jacobian. So this tangent vector is linearly independent of all the rows of the n rows above, and so the whole matrix actually has a rank of n plus 1, and is not singular. And if it's not singular, it's invertible, and that means we can actually follow that branch smoothly. The implicit function there tells us that there's a unique smooth branch going along here, even though we're actually going eventually around this bifurcation point. So let's illustrate what's going on here with just performing the first iteration in this, a first step in the Newton iteration. So we're trying to solve h of y and s equals 0. And we have a solution y0, which is x0, lambda 0. And we have that y0 satisfies f equals 0. Okay, so if we now do a Newton iteration on this expression, starting from y0, we get that we have to solve the equation h Jacobian with respect to y, evaluate it at y0 and s. That's where we want to go, right? That times y at the first iteration minus y of 0 is equal to minus h of y0 and s. Okay, so now what does that mean? If we plug in what we know about y0, hy consists of these 4 blocks. So let's first write down the upper block and then the lower block. And so what is the upper block? We have fx times x1 minus x0. We have to be careful with the transposes. These are rows, so these should be columns. Plus, then comes f lambda times lambda 1 minus lambda 0 equals, and on the right-hand side, we have f evaluated at this point, but we just said that this actually is 0 because we're starting from a previous solution. So this is actually 0. Well, this means that, again, what we have here is this Jacobian, this is just the equation for the tangent, right? That was the same equation we had above, how we defined the tangent here. So that means that x1 minus x0 and lambda 1 minus lambda 0 actually are proportional to the tangent vector. So if x1 minus x0, lambda 1 minus lambda 0 is some number alpha times tau at the point S0. And then the other equation, the second equation is, where is it? Tau x times x1 tau lambda. Okay, let's write that down. We get tau x times x1 minus x0 plus tau lambda times lambda 1 minus lambda 0 is equal to s minus s0, right? We were setting h equals, no, sorry, pointing to the wrong thing, saying the correct statement, but so we have now this term equals minus h, and minus h is this term evaluated at x of s0 and lambda of s0. So both of these terms vanish, and we're only left with s minus s0. And so we have minus that, so this gives a plus s minus s0. Or in other words, since x1 minus x0 and lambda 1 minus lambda 0 is actually alpha tau, this just on the left-hand side is simply alpha times tau, tau transpose equals s minus s0. So this is 1 by normalization. And so we see this number alpha is equal to s minus s0. Or in other words, the extrapolation we're doing here, x1 minus x0 and lambda 1 minus lambda 0 is s minus s0 times the tangent. And so exactly the first iteration goes from the previous solution x0 lambda 0 in the direction of the tangent, a distance s minus s0. And that's what we had in mind in this original picture. So we go along the tangent, a distance s minus s0, and end up on the corresponding branch. And so that's the algorithm. And now one has to sort of just implement it explicitly. And there are some more comments in the notes, which I will not discuss right here.